Section 2.2 was about describing sets, and one of the big ideas that we had talked about last time is what sets were and what a null set in particular was. And I think that's kind of where we kind of got left off on. I was talking about that. So we were talking about a set is any collection of objects, and we talked about the elements or the items that are in that set. We had a couple of ways of describing sets, the roster method and set builder notation method, and we had some notations for you to be aware of as you see them. We talked about the idea of of equal sets and of equivalent sets. Equal means exactly the same elements are in them. Equivalent just means they're the same size. And we had looked at the word or the phrase cardinal number, meaning the number of items in a set. We talked about finite, infinite, and we had a lot of fun with empty or null set, right? We had, I think, monsters in my son's closet this semester. That's what we had. And then we had left off on talking about how to find cardinal numbers, that is, to count the items that are in a set, and these were the examples that we had. All right, Venn diagrams was our last piece of information. A Venn diagram is a picture, really, just a picture of sets. And so the rectangle is what's called the universal set. Any sets that are contained inside of it are drawn as circles or ovals. And when you have a set F inside, then the part that's still inside the rectangle but outside of the circle is called the complement of F, or F complement. And what we're going to do next is we're going to describe a set. If U is the set of all students at OBU, and A is the set of those who are graduating, describe what the complement of A would be. So what would the complement of A be? That is the A with the bar on top. Yeah, and we'll be real specific. Brianna, we're going to write down the OBU students. Not graduating. Okay, does that make sense? So it doesn't necessarily have to be numbers. It can be categories. It can be language that we're talking about when we're talking about these kinds of sets. There's nothing special to what we're doing in terms of numerical values per se. We have another type of set that's called a subset. So a subset, if you have a set A and B is a subset of B, then it will be a subset of B if be a subset of A if and only if every element of B is an element of A. Okay, so it's just a smaller collection. So I believe I talked about our diagram last time. If the rectangle is everybody in my family and F is the females, then that means my sister, my daughter, and my two daughters and I are in the circle, and then my husband and my sons are on the outside of the circle in the rectangle, right? But I could create another circle inside of my circle that talks about the females in my family who are under 12, right? So the small circle inside is the females under 12, and it's inside of the circle that's females in the family. It's inside of the rectangle that's the whole family. Okay, so you've got these sort of embedded circles is what you do when you have subsets. Okay, it's just a further isolated description of something that you already have described. The notation for that, I'm writing the notation for B as a subset of A. It looks like B. It looks like a sideways C or a sideways U. Okay, a C or a sideways U with a line underneath it. Okay. And the way we read this is we can read B as a subset of A. That's okay. But we often will also read B is contained in A. It's contained in it. And if you think about that embedded circle picture, you can kind of see why we would imagine it that way. It's inside. Now, a proper subset is where it truly is not the same as. So sort of the default definition, the way we just defined subset, is I could define the subset, the females in my family who are under 12, but I also could define the females in my family that are under 40. And if I did that, it'd be the same set, the females in my family, because no one in my immediate family is over 40. Okay, so it would just be sort of another name for the same group of people. And by default, it would be called a subset. It just would be a highly uninteresting one because it's the same as the one I already had. Does that make sense? So what a proper subset is a proper subset is actually a subset that really is smaller than the set you talked about already. So for all subsets A and B, B is a proper subset of A if and only if B is a subset of A. So this is one of the conditions. It has to be a subset. Obviously, it's not a proper subset if it's not a subset at all, right? And there is at least one element of A that is not in B. Okay. In other words, the set itself had to be slightly larger. So when I used the description of the females that were under 12, there would be two people still that did not fit in that little bitty circle, myself and my daughter Lalise. We would be in the bigger outer circle. There was at least one, and namely in my example there were two names or people, elements that would be in the bigger outer circle A than wouldn't be inside this little small circle B. That's what a proper subset is.
How will it ask us questions on these?
We're going to do some examples.
Okay.
I'll show you. So the notation for this looks much the same, but you notice it doesn't have the line underneath it. One of the ways that I kind of think about that is that line underneath it is kind of like the line underneath the less than and the greater than symbols that we use in algebra. You think about less than or equal to, greater than or equal to. That line underneath it means they actually could be equal. And that's really what it means here too. On the first one, it's a subset that could be equal. On the second one, it's a subset that can't be, because that line is not underneath it. Okay, so that line underneath it gives it the ability, doesn't mean it has to be, but it gives it the ability to be equal and still count. Okay? And then we can also talk about how we would count the number of ways we could create subsets. So if a set has n elements, then there are 2 to the n power subsets. And one of those subsets is the set itself. So if you want to know how many proper subsets there are, there's 2 to the n minus 1. Just one less. So I'm going to do an example of the subsets of my example 5 here, and then we'll talk about how we create subsets if we were to actually like list out all the subsets, what that would look like, what that would mean. Okay? So taking a look first at this one, it says consider the set of all mathematics faculty member at OBU. And if you didn't know, there are actually 5 of us. So the first question says, how many different subsets are there of the math faculty? So if you were told some math faculty got together, how many different ways could that happen? That's the idea. Okay? So according to the theorem we just saw before, this would be 2 to the n. But what is n in this case? 5, because it said there are 5 math faculty. So this is really 2 to the 5. What is 2 raised to the 5th power? 32 is correct. So there are 32 different subsets of math faculty. Let me do part B, and then we'll talk about how you could actually list them if that were what you were actually looking to do.
Where did we get the 2? Sorry.
It is in the formula over here.
Okay. So it's always 2.
Mm-hmm.
Okay.
It's always a 2. Yeah. How many proper subsets are there? 31. It's just one less. Okay, so no matter what you have, it's just one fewer than what you had before. Because what it excludes is the possibility that it was actually everyone. That's only one possibility.
It wouldn't be n minus 1, so it wouldn't be 2 to the 4th. You take
No.
the 1 off your...
Take a look at how this is written.
Okay, I read
Yeah.
it wrong.
Yeah, the 1 is actually down on the baseline, not up with the exponent. It's a good observation.
So how does that fit back into like the truth of the problem? Because if 2 is just values for everything, what does it mean to say that there are 32 different subsets and there's only 5 of you who are in the math
Right,
faculty?
so I'm going to write out some of these subsets so that we can do it. So let me see.
Is that like in this context? Is that like all the different classes you teach?
M-A-H, no. T and B. Okay, all of your math faculty have different last name first letters. So we have Dr. Hands, Dr. Marsh, Dr. Auk, Dr. Tucker, and Dr. Bond. Oh my goodness, do you see math in there? Wow.
That's what I thought you were
I'm
doing.
totally going to have to tell my math faculty that isn't that interesting until we hired Dr. Bond, and he was our last hire. So, okay. So what would a subset look like? Well, a subset could just have one person in it. So like when I sit in my office for office hours, I am a subset of the math faculty, all by myself. If I write me in curly braces. I know that sounded funny, but a subset is always written as a set, so it's always written in curly braces. So any of our groups that have just one person in it. I'm not going to write out all of these, but I'm going to show you how we're going to do it, okay? So this would be one possible or 5 possible subsets. Another possible subset would be to put 2 of us in the same room, right? Dr. Marsh and I. So we would take every group of 2 of us at the same time. Now notice I don't want to write M, H, and then also H and M, right? That's the same collection. Changing the order doesn't matter if I write it as MH or as HM. So I would write all of the groupings of 2. So these are groupings of 1 person. These are groupings of 2 people. What do you think I'd do next? Groupings of 3 people. And then what would I do? Groupings of 4 people. Hang on, I'm going to move this down just a little bit so I'm not writing into my words. I don't know why I did that way, but... Better. Okay, so groupings of 3 people, like for instance, maybe it's all 3 of the females. Maybe it's Dr. Marsh, Dr. Hands, and Dr. Tucker. Okay? And then I could do groupings, like you said, of 4 people. So maybe it's, let's see, if it's the oldest 4, I think we have to leave out Dr. Tucker. So we could do Dr. Bond, Dr. Hands, come on, right. Dr. Marsh, and Dr. Auk. Okay, so any groupings of 4 people would be included. And then there's actually 2 groupings that we haven't included yet. There's the grouping of all 5, which wouldn't count as proper, right? But it would be a subgroup or subset, excuse me, by definition. It sort of is the weird one that gets by it without really meaning to. It is a subset, it's just not a proper subset. There's also the possibility of a subset with nobody in it. What is that subset called? The empty set. And by definition, it is a subset. So let me go back to the definition so you can actually see how that works. For all sets A and B, the empty set is a subset of A if and only if every element of the empty set, for which there's none, is an element of A. So do you see how it sort of fits by default as well? Every element of the empty set, for which there's none in the empty set, are also in set A. So the empty set gets to be a subset from every set as well. And if we wrote them all out and we counted them all up, we would end up with 32. And then if we eliminated this one right here because it's not proper, it's the one not proper subset, we'd end up with the 31. So I don't know about you, but I don't want to write down 32 of these guys. I wrote down several already, but do you see the sense of how you would do it if you were dealing with a smaller group, maybe?
So like
Smaller set.
when you were making out, like to make those other ones, you would just do different combinations of people?
Well, it depends on what the elements of your set are. So yeah, if your elements of your set are people, then yes, you would do different groupings of people.
So you should be able to come up with like 30, you already did 4, so like 28 more.
Yeah, I have a whole bunch of them on here, but not all of them. There's plenty more on here, groupings of 2, groupings of 3, groupings of 4.
Right?
I already wrote down the groupings of 1.
So you, okay.
Yes, but yes, we would write down any groupings of 1, 2, 3, 4, or 5 or 0.
Okay.
The 5 and the 0 are the uninteresting ones, but they get to fit by default. Okay, is everybody good with the idea of what we're doing here? Okay. And again, you could talk about, for instance, you could use this for like creating a committee, right? How many different ways could you create this committee? Well, it depends on how many people you want on it, right? That kind of thing. You could talk about subsets in that way. All right, so now let's suppose that we have a set and we don't know how many are in it, any elements are in it, but we do know how many proper subsets there are. We should be able to use that same formula to find out how many elements are actually in the group. Okay, elements are in the set, I should say it that way. So our formula for proper subsets, because this does say proper, is 2 to the n minus 1 equals our number of proper subsets. Right? And this problem tells me, sorry, I put the -1. Even after having talked to you guys about that, I put the 1 in the wrong place. Oh, make sure you erase it. Hurry, hurry, please. Oh, bummer. Totally didn't do that right. Please, 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 please fix it. Okay, this is equal to 63. Right? So what would I do to figure out what n would have to be? You can add the 1, either in your head or on paper, either way. 2 to the n equals 64. And then for the purposes of our discussion here, we just need to figure out what the n value would be, and it has to be a whole number. I mean, it's a number of elements in a set. You can't have half of an element in a set, right? That doesn't work. So you can play around with your calculator to figure out what it is. Maybe it's a number you're already familiar with and aware of and you know. Does anybody know what the n value should be in order to give me 64 here? It can't be 3. 2 to the 3rd is 8. 2 to the 5 is 32. 2 to the 6th, will that do it? Yeah, it is 2 to the 6th. So n is equal to 6. I think you were thinking of 8 squared instead of 2 to the 8th,
Yeah.
probably. Yeah. So this one's 6. This tells us that if you had 6 elements in the group, there would be 64 subsets. 64 subsets, 63 proper subsets. The way the problems work. For what we're working on, so the answer to your question is yes, there is another way to do it, but the real answer for what we're doing is that we're not going to explore those options too heavily, okay? The numbers will be small enough that guess and check's not going to be difficult. If you guess something too large, you're going to get way too many. If you guess it too small, it's going to be way too small. All right. What I'd like to do next is I'd like for us to take 4 examples, and we're going to identify in our examples whether the symbol that's, what is this symbol? We did this one last time. Do you remember what that symbol that's got curly E is? Element, actually. So this is the is an element of. And I didn't define this last time, but I'm going to guess that you can, put 2 and 2 together. And what do you think? Yeah. This is not an element of. Right? You draw a line through something, it becomes the word not. Yes, ma'am.
Is it supposed to look like what's on there? Because I've got exclamation.
Yes, I have absolutely no idea because I save them as PDFs so that all my math symbols should be preserved. And then for whatever reason, there are some computers that print them out weird.
Okay.
And it doesn't even make any sense because the PDF that should never happen. So I don't know why. But please change them. Yeah, gobbledygook. This happens every semester. Somebody gets gobbledygook when it prints them out. I don't know why. If you're looking at me like, what is she talking about? Then, your paper probably looks fine. There's no problems. So, yay for you. Okay. So, yes, they should look like the symbols and things that you see on the screen. This is what your paper should look like. So, we've got is an element of, and we have is not an element of. Okay. So, we're going to go through this list, and the question we're asking ourselves on every question is what's on the left an element of what's on the right? Not a subset, an element. Okay, so be really careful. We're going to do this again in a minute with subsets, but we're doing it with elements now. So on the first one, it's the empty set on the right, on the left, and it's the set with the number 0 in it on the right. Now the first thing I want to make sure that you understand is these are not the same set. Correct? Empty set on the left, the set on the right has something in it. It has one element in it, 0. So these are not the same set. But is it an element? Okay, Ashley is correct. It's not. Do you remember why, Ashley?
Because, I just remembered that, we had, with the 0 with the line in it, is the same thing as, it just had the curly cues with nothing in it. So if 0 is in it, then that's an element. Whereas if it's a null set, then there would be no elements in it.
That's going to make it not equal. But that wouldn't make it not an element, actually. But that does make it not equal. You're right on that fact.
But then 0 isn't counting, or no, a natural number?
Nope, that's not why. It's a good guess. Think about the language that I used when I described the thing on the left. What did I call it? An empty
Null.
or null set. Did you hear that word set? A set is not an element.
Oh, well.
It's a set. Are you guys with me?
Yeah.
It's not an element at all. So it has nothing to do with what's over on the right. No matter what I put over here, I have to put not an element there because it's not an element of any set because it's not an element. Right? It's like saying, if I asked any one of you, because you're all female, if I asked you, are you a male in the Miller's family? Well, the answer is no, and you knew before I said Miller's, right? It doesn't matter whose family I listed next. You're not one of them because you're not a male. The same thing's happening on this. It's not an element of whatever happens on the right because it's not an element at all. Now, the second one on part B, 15 is an element, right? And the reason that I know is because it's not the null set, and it also doesn't have the curly braces around it. When I put the curly braces around it, that's what makes it a set. Okay? The 15's all by itself stand alone. There's no curly braces. So when I'm looking at number 15, it is an element. Now we just have to figure out if it's an element of what's on the right. Do you see how the discussion's different? So it would be like you asking you now, are you a female in the Miller's family? Well, now you have to listen to which family I'm talking about, right? Because you sort of satisfied the first word, you're female. We just have to figure out if you satisfy what's coming next. So this one, 15. Yes, it's an element, but is it an element of what's described on the right? So you might have to think about what is what's on the right describing. What is that? X, but what is X defined to be? 2 times n. What kind of numbers are those? Evens. And if you weren't sure, could you figure it out? This says natural numbers. We defined those last time. That's like 1, 2, 3, and so forth. And this is saying that I need to take all of those natural numbers and multiply them by 2. So when I look at 2n, so these are n, when I look at the items that are 2n, I get 2, 4, 6. I get even numbers. Is 15 going to fit into that description? No, it isn't. 15 is not an even number, and what's on the right is even numbers. So this is not an element of that set. How about let's see.
Yes.
Oh, say that really loudly, Kelly.
I said it would not be an element of it because 4 is a set.
Right. The notation that's used on the left is set notation. All right, we're back to the argument about you guys being males. We don't have to care what comes next. You're not a male. This 4 inside the curly braces, all of that notation is notation for sets, not for elements. So this is not an element because it's not an element of anything. Man, I hope we finally get to write element down on D. Do we?
Yes.
Is 16, as it's written, an element? Yes. Is it an element of what is described on the right? Yes, because that's another description for even numbers on the right, isn't it? And this one, 16, is an even number, so this one works. Now, your book's going to just have you fill in blanks like this. I would encourage you when you're going through them to make sure that you have a justification in your mind about why they are or they aren't. Because when I ask that kind of a question on a test, I make you justify it. Right? So the justification on the first one is that the empty set isn't an element at all. Same thing for the justification on the third one. The set the number 4 in it is a set. It's not an element at all. But the justification on part B looks quite different. It is an element, but it's not an element of what's on the right because the right is even numbers. Yes, Ashley?
So do you want us to go ahead and justify it whenever we're doing our homework?
You don't
Or
have
if
to.
It doesn't say we don't have to do it. as
You
long
don't
as
have
we're
to.
doing it.
But make sure that when you're doing it, you have a justification in your mind. If you want to write it down, that's totally great. But just please make sure that you are very clear on why you're choosing what you're choosing. Does that make sense? Okay. We're going to use all of the same problems, but the directions have since changed. These directions say that we're going to use symbols of subset notation. The first notation right up there means it is a subset of. And the second one, again, I haven't defined it, but I know you guys are brilliant and you know exactly what that means without it being defined. What does it mean?
It's not
It is not a subset of. Now, inherent in the words that we're using, that is the word subset, we have to understand that the first thing it has to be then is a set. If it's not a set, it's not a subset. Like on the last slide, if it's not an element, it's not an element of what comes next. The first issue is it a set? The second issue is it contained inside the other one? Okay? So as we're looking at them, the first question we should be asking ourselves as we encounter them is this a set? So let's ask ourselves for part A. Is the 0 with a line through it a set?
Yes.
Yes. It has a special name. It's called the null set or the empty set. It is a set. So it passes the first criterion. The second criterion is it contained in it? Is it an actual subset then? Okay, the definition for subset secondly said, every element in it is an element of the thing that's on the right. Careful. Flip back to your example of the math faculty. I wrote it, didn't I? Yeah, right over here. Jot yourself down a note. The empty set is a subset of every set. It's not exciting, it's not interesting, it's highly unhelpful, but it fits the definition by default. Every element inside of it, for which there aren't any, are inside of the second set, no matter what that second set looks like. Because there's nothing in the empty set. It's almost like saying that I'm a member of my own family. Well, yeah, that's sort of obvious, right? It sort of happened by default. So this empty set is in fact a subset of anything. So the reality is no matter what is on the right-hand side, the answer here is going to be, I'm sorry, I wrote the wrong symbol. The answer here is going to be subset. Please make sure you have the right symbol written since I wrote it incorrectly first. No matter what is on the right-hand side, it is a subset. Okay? Yes?
So like words, like you used like the babies in your family
Mhm.
last time, and you said that because there's no babies in your family. So like technically the babies in your family are still a subset of your family, even
Correct.
though there's none.
That's right.
So
The
really
babies in my
anything that
family.
you don't have in your family could still be a subset of your family.
Certainly. That is a very true statement. Did everybody hear Ashley well enough on that? We talked about last time, I gave the example of the babies in my family, the infants in my family, and they were fantastic, right? Remember how wonderful my infants are? Okay, just checking. All right, so the infants in my family are still a subset of the people in my family. There's nobody in that set, but they're still a subset of the people in my family. Okay? How about the second one? It's not. Why not?
Because contained is an element, not a set.
Right. This one fails because the thing on the left, that is the number 15, is an element. If it's an element, it's not a set. And if it's not a set, it's certainly not a subset. Okay, how about C?
No, because, or doesn't it have to be that every element from B is in the one on the left?
I think you've got it backwards in your mind.
Okay.
Yeah,
It's every element from A.
right. It's every element from what's on the left has to be in something on the right. So let's define or describe. First of all, is it a set? Yes. So we kind of passed the first benchmark, right? We do have a set on the left. Now the question is everything in it? And there is only one thing in it, yeah? The 4. Is it on the right-hand side? Where? It's the 1 plus 3, right? This is not particularly helpful way, but it is another way of writing the number 4. So this set on the right is really just the items 3, 4, 5, and 6. So is the set on the left, that is the set with the number 4 in it, have every element in it inside of the set that's on the right? And the answer is yes, it does. So this is a subset. Yes, ma'am.
Talking in terms of like the definition, is set B on the left side and like A on the right side?
Yes,
Okay.
from the
Is
way that we had
basically
defined it before.
A was the one on the left and B was the one on the
Yeah,
right?
it's always the smaller, if they're not the same size, the smaller one is on the left.
Okay.
Yes. How about D?
No.
No, what's wrong with D?
It's not.
It's an element, not a set. Okay. These are kind of weird. There's several things you have to sort of keep your eyes open for, to be mindful of, to be watchful for as you're working through them. So do keep those items in mind as you're working on them. All right, the fundamental principle of counting, or the fundamental counting principle, says the following. If an event capital M can occur in little m ways, and an event capital N can occur in little n ways, then event M followed by event N can occur in mn ways.
There's a capital N. Just make it a little N.
They should be like they are on this. Are you telling me there's a typo on a piece of paper?
Yeah.
Fabulous. I'll get it fixed later. There's a capital M for event. There's a capital N for event. And then it's little m and little n for the number of ways.
Okay.
This is the third semester that I've used these notes, which means that it has been wrong for 3 semesters and nobody has told me. So thank you so much for letting me know. I'll get them fixed. Okay, does everybody have them correct now?
Yes.
Excellent. All right. We used this last time, and we did an example, and I didn't really justify why I was doing it, so I'm going to go back now and make mention of it so you can see that we used it and that we really are allowed to. This was the example where we used it. And the description where I talked about was, I said that we had 6 gentlemen in the room, and the first lady came in and she had 6 choices, right? And we wrote down 6. And the next lady came in the room and she had 5 choices, and we wrote down 5. And then in the end, what I said we needed to do, and nobody asked me why, I was actually kind of glad since we hadn't gotten there yet, is we multiplied them. And the reason we multiplied them is because this is what you do when it's the fundamental principle of counting. Fundamental principle of counting is that you multiply those options together. And you'll notice the fundamental principle of counting just gives it as an example for 2 items. We did it in this problem for 6. That's okay. We can do it for as many items and many choices and many events as we need to. We got an example. I think the example's Pizza Planet, is it? Nope, it's not.
Pizza Planet is proportional.
Oh, different class. I have Pizza Planet for my example. What a shame. All right, well, you guys are all ladies, so maybe it will work anyway. We have shirts and skirts and shoes, and I know we all get dressed, so it fits. How many different outfits can be created from 3 shirts, 4 skirts, and 5 pairs of shoes? Assuming they all match, of course. That's the understood underlying thing here. All right, so we actually have 3 things that we're choosing. There are 3 events. There's the event of choosing a shirt, an event of choosing a skirt, and an event of choosing a pair of shoes. Because if you didn't have one of all of those things on, it would be a problem, right? Yes. Presuming that there's no other clothes that you have with you. Okay, so there are 3 options for your number of shirts. There are 4 options for your number of skirts, and there are 5 options for your number of shoes. And then what does the fundamental principle of counting say I do with these numbers? I multiply them. And if I multiply 3 times 4 times 5, what do I get? 60. So there are 60 outfits. Okay, another example, because we like to shop because, I don't know, I think it's in our DNA. Is that true? Sure. Okay. You have 6 favorite stores in the mall. In how many ways can the following happen? The first one says you have time to go to only 3 of them. So if I have time to go to only 3 of them, there's only 3 events, right? So the way that I'm drawing them, there's only 3 lines that I'm going to draw on here because there's only 3 stores, there's only 3 events that I'm going to do. My first event, how many choices do I have to go? 6. And presumably we didn't go to the store, leave, and then come back in the store, right? So my second choice there are 5. And then my last choice there would be 4. So what is 6 times 5 times 4? 120 not stores.
Options.
Ways, options, something like that. There are 120 different ways I could go, or different groupings of stores I could go to in some kind of an ordering. What if you had time to go to all 6 of them? Yes, then there will be 6 events. And we will have 6 times 5 times 4 times 3 times 2 times 1. And it will be just like the problem that we had before, where I described it as the gentleman in the room and the ladies coming in and selecting one to go on a date or whatever, right? 720. There are 720 ways you could go to all 6 of your favorite stores. And then we already did example 11 last time, so you should have that one already filled in. What?
That's why we're so indecisive, because we have 700.
So many choices.
Different ways
I
to
know,
choose. Give us a
absolutely.
break.